Three, two, one. All right, and we have made it to the end of Math 2070, the online section. Thanks for sticking it out. And we'll wrap up the course with a review of maybe the greatest hits of this matrices and linear algebra course. So, let's recall, sort of big picture, what's ultimately been our goal here. Well, we've been trying to understand the behavior of the mathematical object known as a system of linear equations. And here is generally what they look like. These are pretty pervasive in mathematics. Before you got to this class, you've possibly encountered them, depending on your math journey up until this point, but now we're pretty comfortable with things that look like this and how to solve them and the various theoretical aspects buried within these equations. Okay. All right, and again, let's read these equations a little bit more carefully. What's going on here? I have unknown variables, x1 to xn, that I would like to know the value of. And what I do know are the coefficients associated with the x variables, so the numbers that are multiplying them. And on the right-hand side, I have these singular values, b1, b2, all the way to b3. Okay. Now, as we noted, this becomes the matrix equation, ax equals b. And what's nice about this is that this converts this collection of equations into a single equality. And what's even nicer is that the way it is turned into ax equals b is by grouping together the various types of symbols that were showing up here. So we have our vector x consisting of the unknown quantities, so our usual favorite symbol in math for an unknown object. On the right-hand side, we have all of the b terms, and the a corresponding to the things that are multiplying the unknown variables we're looking for. All right, sweet. All right. And as noted, once you sort of take your system and convert it to this matrix equation, it is then nice and easy to apply row operations to arrive at solutions. So, for example, here I have a system of 3 equations and 3 unknowns. I can isolate the coefficients on the unknowns x1, x2, and x3. So 1, 3, 5, 1, 4, negative 8, negative 3, negative 7, 9. There we see those as our matrix. And then our right-hand side, 4, 7, negative 6. And as we noted, you can take the matrix of coefficients and the right-hand side and smash them together, put a bar between them, and sort of a facsimile, if I got that word right, probably not, of the equality sign. And now in this form, row operations can be performed, which again are scaling a row, scaling and adding a row, and swapping rows. And doing that can get it into the reduced row echelon form. Echelon, meaning that I have this staircase pattern with my leading coefficients. Reduced in that the leading coefficients are the only non-zero things appearing in the column. Recall that this here and that there is then a pivot column, column 1, column 2. All right, and in this form then, I can read off to you here in the top equation that x1 must be negative 5 minus 4 x3. There you go. Right, wouldn't be a final video if there wasn't a mistake that I had the correct live. There it is. All right, so the minus 4, the x3 over there. All right. And likewise, x2, add this 3x3 over, solve for that, and pull it apart accordingly. x3, of course, did not show up to the party. There's no pivot column associated with the third column, so the third variable, x3, is in fact a free variable, as we see here, and ends up being the parameter that shows up in our system. Hey, there we go. All right, so there we go. We have solved our system of linear equations using row operations. Okay. Now, right, as we started the course was, hey, I want to learn how to solve these things. And as we see, there's, right, they can just be solved algorithmically. You just set up the stuff, and you do your row ops, and you call it a day. But that's not the full story. It's only part of the story. Even deeper is all of these sort of theoretical aspects and the other algebraic machinery that is surrounding this system of linear equations. So let's talk a little bit about that. Now, the natural approach, God, some good spelling there, for solving for x in the equation ax equals b, right, if I didn't tell you anything about that and I just gave you, hey, ax is equal to b, solve for x, the first thing your math lizard brain would want to do is divide the a over. But, context here, this is matrix multiplication, and that does not follow the usual rules of multiplication, as we noted. It is not commutative. It does not have cancellation. You can multiply non-zero things and get 0. Matrix multiplication has weird things going on, so you can't just divide. We need to be very careful about what we mean by, alright, I want to solve for x here. That means I need to get a off of the left-hand side of the equation. And the way to formally do it is that, well, a matrix is invertible if there is another matrix, a to the negative 1, with the property that multiplying a on both the left and the right by this matrix gets us the identity matrix, the matrix with 1 on the diagonal and 0 on the off diagonal, anything off of the diagonal. All right, and oh hey, look, this formula shows up a lot, not just in this course, but in math in general. This is the Kronecker delta function. Pretty exciting. All right, and note that now that you know multiplying by A inverse will give you the identity matrix, and the identity matrix is, as its name suggests, multiplying by gets you what you originally multiplied by. It acts as the identity. You can simply then multiply both sides of this equation by A inverse, and then you have a formula for x. Great. So naturally then that asks, all right, well, when is a matrix invertible, and how do we compute the inverse? And as you may recall, we did a whole big old video about all of the various equivalent conditions that ensure a matrix is invertible. And one of them that is quite useful, we'll talk about a few other ones as we go throughout the rest of these slides, is that you are invertible precisely when you're row equivalent to the identity. So in other words, your reduced echelon form is the identity matrix. And note, the matrices here have to be square. They have the same number of rows and columns. And since you're row equivalent to the identity matrix, that means that since row operations are in fact matrix multiplications, keeping track of the row operations that turn you into the identity will give you a method for actually computing the inverse. So specifically, if I take a matrix here, and I want to know if it's invertible or not, I augment it, as we do, with the identity matrix on the right, and then now I'm going to perform row operations, and the row operations that turn this into the identity, or something else, will affect the identity matrix over here. And if I do indeed get the identity matrix on the left, then the resulting matrix on the right is all of the multiplications of the row operations, and those would have to then be the thing that multiplies b to get us to the identity. So what we end up with on the right is indeed the inverse. And if we compute the reduced row echelon form of this matrix, which I already did, and by I mean I asked a computer to compute this for me, we see that indeed I got the identity matrix on the left, meaning that my original matrix is row equivalent to the identity, and thus the thing on the right must be the inverse. Exciting. All right. So, before moving on, let's note that there is a classic formula. If a 2x2 matrix is invertible, which happens precisely when AD minus B is non-zero, when its determinant is non-zero, then the inverse can be computed by doing 1 over the determinant times this magic matrix, where I've swapped the diagonal and negated the off diagonal. And as we learned, this is the adjugate matrix. Pretty cool. So, as I mentioned, I think when we first talked about this formula, this is an incredibly important one. Put this in your brain, in your mind palace, right next to the quadratic equation. It's on the same level of, like, applicability. Cool. All right. So, that's the story of invertible matrices. Note, it gave us, again, another way of solving. But as we already saw, when you solve a system of linear equations, it's possible that there is these parameters that show up. Right, there's sort of some degrees of freedom, and it'd be great if we could understand more intently how that degree of freedom situation is going to work. So, note that our parametric form of the vector solutions was built off of elements of Rn, Euclidean space, so lists of n real numbers, which we typically write horizontally, vertically the other way. You can also write them horizontally, it doesn't really matter. Right, where you have an x1 and x2, the general element being denoted by x sub k, and all the way up to the last one, x sub n. Now, one of the algebraic features of the set is that I can scale and add elements, and it is done component-wise. Scaling a vector just means scale all the entries. Adding two vectors means add up the entries. Okay. And as we noted, this is not the only math object with such operations. Matrices can also be scaled and added, and so can functions, right? You see that in calculus. We talk about sums and scalars and products and compositions and all sorts of things of functions. And polynomials are our favorite type, and they are our go-to example for extra fun things in this class. Now, because we have observed scaling and adding in different scenarios, we would like to capture the scaling and adding behavior on its own. So that introduces the idea of a vector space, which is just a set where scaling and adding are defined and behave the way we want them to. And again, there were 8 axioms for that. And the benefit of studying scaling and adding in the abstract is that we don't need to get bogged down with the minutia, right? I don't need to worry about, I've got all these entries in my vector I need to keep track of, or, I got all my entries in my matrix I need to keep track of, and, I've got a polynomial, I got all these coefficients, or if I've got some more advanced functions, I gotta keep in mind properties of trig or exponentials and logs. We want to avoid messing around with that and focus solely on how does the scaling and the adding work, and that leads us to the world of vector spaces. All right, now there are a lot of features to vector spaces that are of a lot of importance and were, again, pretty pervasive throughout this course. The first idea is subspace, so these are the subsets of vector spaces that are closed under scaling and addition, and thus become vector spaces in their own right. So these are the wheels within the wheels. All right. Now, a great example of a subspace, one of the fundamental subspaces, is the null space of a matrix, the set of vectors x, so that a times x is 0. Or another way of looking at this, the set of solutions to the associated homogeneous system of linear equations, whose coefficients are the entries of the matrix. Another fundamental subspace that we saw frequently throughout the course is the column space. So the set of vectors b, so that b is actually equal to a times x. And while that's a nice definition for column space, there is a better one. That leads us to the next feature of a vector space, span. The collection of linear combinations of a list of elements, and we write that as a span of those elements right there. And note that the column space, hence its name, you can think of it as the span of the columns of the matrix. And as we recall, that's sort of our definition of matrix times vector. You take the columns, you scale them by the entries of x, and add them up, and thus B would have to be a linear combo of the columns. Cool. All right, now something we learned about span is that span is not always efficient. Sometimes a span of a list of things has some redundancy going on, so we would like to have the case of a span that is efficient, and that leads to linear independence. So specifically, if I know that my linear combo is trivial, meaning that I scaled and added and got the additive identity, then the only way I could have pulled that off is if my scalars were equal to 0 in the first place. So in other words, right, there's no linear dependence on the elements x1 to xn. Scaling and adding and getting 0 can only be done with 0 scalars. Note, if I can scale and add and get the 0 without 0 scalars, I can isolate a non-zero one and rewrite that element as a linear combo of the others, so the span would then have a redundancy. And note, linear independence is a very powerful idea, and it's an idea, again, that we've kind of encountered in our math life. One example is that polynomials have a linear independence, because if a polynomial is equal to 0, then all of the coefficients must equal 0. So we've already sort of seen this in our math life before we got here. And in terms of matrices, linear independence is connected to the null space of a matrix being trivial. In fact, the columns of a matrix are linearly independent precisely when your null space is trivial, meaning that the homogeneous system only has the trivial solution. Cool. And recall that's connected to a matrix being invertible, because of course it is. Alright, so we've now got the concepts of span and, I don't have the slash on the pause. That's, oh my god, hilarious. Good times. Alright, so we have the idea of span and linear independence, and we want to smash those two together, and that leads us to the notion of basis, which is a linearly independent list that spans. And there are many bases and many different ways of finding them, and we will see a little bit later that there is a particular type of basis that we really like because it gives us some geometric information. But the classic example is the standard basis elements in Euclidean space, which are precisely the vectors that have 1 in one spot, and zeros everywhere else. Nothing more, nothing less. And equipped with bases, we can then speak of dimension, which is the number of elements that are in any basis. So, for example, if we look at the set Pn of polynomials of degree at most n, which all look like this is n plus 1 dimensional. Note I have a... I begin by counting at 0 in this case, so there's n plus 1. Note that Rn itself is n-dimensional, so here the notion of dimension, the algebraic notion of dimension, lining up with sort of our intuitive idea of, R2 is 2-dimensional, R3 is 3-dimensional, and so on and so forth. Good stuff. Always good stuff. Alright. So, now that we have ran through the gauntlet of the essential features of vector spaces, let's actually compute some bases for some subspaces, specifically the null space and column space of a matrix. So here is a matrix. To find basis for the null space and column space, you get the reduced echelon form. There it is. I have gotten it there. From this, you can extract the null space by just pretending it's augmented with 0 on the right and solving here. And now I want to double check that I actually solved this one correctly. That one looks right, and that one looks right. Perfect. So note here that we have column 1 and column 2 as pivot columns, but column 3 and column 4 fail. So variables x3 and x4 are free variables, and x1 and x2 can be written in terms of x3 and x4. And hey, cleans up like that. And look, anything in the null space is a linear combo of these two things, and you can do a quick sniff test on these and see that they are in fact linearly independent. There is no way of scaling this and creating that with non-zero scalars. Alright, so we get a basis for a null space. Note, hey, there it is. Everything in the null space is a linear combo of these linearly independent things. My null space is 2-dimensional. Alright, and as we learned, a basis for the column space can be formed by identifying the pivot columns and going back to the original columns of our matrix. Here was column 1 and column 2 of our matrix originally. There they are. And we noted that the pivot columns exist in column 1 and column 2. And there we go. We have a basis now for our column space, and wouldn't you know it, it's also 2-dimensional. Note that if I add those dimensions together, the null space dimension plus the column space dimension, I get 4, which is the number of columns of my matrix. And this was the content of the absolutely important rank nullity theorem, which states that if you have an m by n matrix, the dimension of the null space and the dimension of the column space will always add to the number of columns of our matrix. Very cool. All right. And as we noted when we first got this is essentially the fundamental theorem of linear algebra, because this is dictating exactly why solutions behave the way that they do, why we have sort of these, free variables showing up represented in the dimension of the null space, why there's sort of a dependence on the number of variables you have, the number of columns. And pretty good stuff. And of course, a very favorite theorem of mine, because you can ask all sorts of annoying questions, which may or may not appear on a final problem list, or previous ones as well. Who knows? Alright, so ran through the exciting world of vector spaces, so what's the next thing to talk about? Well, one feature of vector spaces that is worth mentioning, we'll call that AA. A function between vector spaces is called linear if it respects the operations associated with it. Right? And this is in the spirit of the favorite phrase of the mathematician, the x of the y is the y of the x. So here we see that t of the linear combo is the linear combo of the t's. Right, so a lot of maps in your math life are in fact linear. Derivatives are linear. The derivative of a sum is the sum of the derivatives. Integrals are linear. The integral of a scaled function is the scaled integral. So, linear mappings possess a lot of nice properties, and thus will appear in a lot of branches of math. And again, it's part of this paradigm of these are precisely the functions that leave the structural relations of our vector spaces undisturbed under their action. Right, so from the mathematical standpoint, the only thing that makes a vector space is the scaling and the adding. And my function t here keeps those things in place. So I would obviously care about the functions that leave these things undisturbed. And in fact, the big theorem, the only linear mappings between Euclidean space are in fact matrix multiplication, meaning that t of x has to be a times x for some unique matrix A. And as we noted, this A can be computed by plugging in standard basis elements, and those give you the columns, but you can get other types of matrices out here depending if you want to have different bases equipped on your Euclidean space. Now, that then leads us to the notion of the coordinate vector mapping, a very important linear mapping, which we're now going to spend a little bit of time digging into. So recall that if I have a basis for a vector space, then every element has to be a linear combo of these. This is what it means to be a basis. And the linear independent part of being a basis ensures that the scalars are in fact unique, which means that my element x can be represented as an element of Rn. Hey, and not only is this mapping linear, it's an isomorphism, meaning that it's a linear mapping that is also invertible. And again, from the big picture standpoint, the linearity ensures that the vector space structure between these two is the same. The invertibility ensures that as sets, these objects are the same, meaning that the elements of V are just elements of Rn, but they've been relabeled in some fashion. Right, and so as we kind of pointed out, polynomials seem to really behave like Euclidean space. So let's go ahead and compute a coordinate vector for a polynomial. So, first of all, I need a basis. So here is a list of 3 second degree polynomials. This has to be a basis for P2, and the way we can verify that is by first getting the traditional coordinate vectors for these, the coordinate vectors with respect to the standard basis for the polynomials, which are literally just, hey, what's your first coefficient? What's your second coefficient? What's your third coefficient? So 1, 0, negative 1 for our first one, 0, 1, negative 1 for our second, and 2, negative 2, 1 for our third. If we smash these vectors into a matrix, that matrix is invertible, and there's a multitude of ways of computing it. Get its ref, compute its determinant, do whatever you want. Since that matrix is invertible, the columns must be linearly independent, meaning that my original list here is linearly independent. And since P2 is three-dimensional, any linearly independent list of 3 things must be a basis. If not, then we could extend it to a larger linearly independent set, but that would violate the dimension theorem, telling us that if you've been spanned by 3 things, your linearly independent sets can only ever have at most 3 things. Beautiful. Alright, so now we know it's a basis, so let's actually go ahead and compute a coordinate vector. So I picked some random thing here. And recall that the coordinate vector of this is precisely the vector, so that when I multiply it by the matrix formed by taking the standard basis elements for our original polynomials and making them a matrix, multiplying this vector by that matrix has to give us this one right here. That's just how it works. And thus you need to simply solve for this vector by any means necessary, so you can get the inverse and multiply by it. You can set up the augmented matrix and perform the row-ups, and solving it will yield 7, -3, -2, and thus we've got our coordinate vector. And hey, there we go. Good stuff. Alright. Now, what else do we got to talk about? Well, I have two more big ideas, and let's talk about probably the biggest idea, which is the notion of eigenvalues. So eigenvalues are incredibly important. As we mentioned, this little equation right here is why Google became synonymous with performing a search on the internet. And note, as an equation, right, it's simply saying that the action of matrix multiplication on your vector is the same thing as scaling. But note the highly important fact that the only way you're an eigenvalue is if there is a non-zero vector where this works. Obviously, if you drop this requirement, then everything's an eigenvalue because you can always find the zero vector, which will multiply and scale always to 0. All right. Now, note that if you subtract this over here, it factors into this formula right there. And hey, since v is non-zero, that means the null space of A minus lambda I is non-trivial, and thus this matrix cannot be invertible, meaning that its determinant must equal 0. So if you want to compute the eigenvalues for your matrix, here is the formula you need to solve for. And as we mentioned, this is a polynomial whose degree is the same size of the matrix. Good stuff. So, actually computing the eigenvalues and finding basis for the associated eigenspace boils down to first getting the eigenvalues by getting the roots of this polynomial, and then getting the basis for the null space of the associated matrix. Hey, good stuff. Alright, so let's do a 3x3, and I picked a particularly sobering 3x3, because there are no zeros, so if I want the eigenvalues, I gotta subtract lambda off my diagonal, that's that A minus lambda I, and then take the determinant, and I've got no choice but to do a full-on determinant. So I particularly did it across the first row, note the plus minus plus paradigm, and note the deletion of rows and columns. Alright, and then you gotta do all of these 2x2 determinants, and you get this big sprawled out mess. And in the type notes that I posted, I have the full-on computation, but after a bit of work, you can clean this up and find that you get lambda minus 1 quantity squared and 5 minus lambda as your polynomial factors. So this reveals that our matrix has two eigenvalues, 1 and 5, and 1 is interesting because its algebraic multiplicity is 2. It shows up as a root of the polynomial twice. And as we mentioned when we first encountered these sorts of things, it's possible that your algebraic multiplicity is 2, but your geometric multiplicity is less than that. The geometric multiplicity coinciding with the dimension of its eigenspace. So let's go ahead and get the eigenspace for lambda equals 1. I'll leave it to you to get the eigenspace for lambda equals 5. So indeed, subtract 1 at the diagonal, and then look at the null space equation. That's this one right here. Note that I only really have one equation to work with. I have v1 plus 2v2 plus v3 is 0. So I can just solve for v1, and I have two free variables. And hey, there we go. Great. Right now, of course, you could go for the whole augment and do your row ops, but because I've got 3 rows repeated, I really don't need to go for that process. I can just go, hey, this only has one equation, and I can get v1 in terms of v2 and v3. Note these are two linearly independent things, because again, good luck scaling this one using a non-zero scalar to get the other. And hey, I have a basis now for my eigenspace, and looky-loo, it is indeed two-dimensional, so this eigenvalue is not defective. It has the same algebraic and geometric multiplicity. Cool. Alrighty. One last thing to discuss, and that is some geometric things. Recall that the dot product of two vectors, x and y, is the real number formed by multiplying the coordinates together, x1, y1, x2, y2, all the way up to x, n, y, n, multiplying them up and adding them all up. And this algebraic operation has geometric powers. So, for example, if we know the dot product here is 0, then I know that my vectors are perpendicular, right? And you can simply draw this out in R2 and convince yourself it's true. You can pull some extra trickery and get the law of cosines to help you out, which is what we did. And note that this notion of orthogonality for two vectors can be extended to a whole list. So indeed, if you have a list of vectors, these will be orthogonal precisely when their dot product is equal to 0, when j and k is not equal to each other. Oh, hey, look, it's part of the Kronecker delta. I wonder what happens when the dot product is equal to 1 when j and k are equal to 0. Maybe things get a little normal. All right, well, one of the features of orthogonal elements, which we sort of set up earlier in the talk, is that indeed they are linearly independent and thus will form a basis. Sweet. And in fact, you can do one better. If you have a orthogonal basis for a subspace, then any element, no, it doesn't have to be in the subspace, any element, we can create its projection by computing these specific dot products and scaling our the elements v1 to vm by them. Again, note dot products are scalars, not vectors. And as we saw, this vector has a boatload of incredibly nice properties, and probably the big one is that it's the point in the subspace closest to the original point x. Note that if x was already in the subspace, then its projection would in fact be this linear combo. So, because it has this very geometrically advantageous property, which we saw this ends up being the basis for how least squares works, I would like to be able to compute projections for any possible subspace, and in least squares, we sort of circumvented actually having to do any sort of crazy computations by pulling some matrix trickery. However, in general, if you want to compute your projection, one method of getting it is using the Gram-Schmidt process. One possible method. Possible, oh my god. How many spelling errors were there in this video? I don't know, man. I don't got a doctorate in words. I barely got a doctorate in math. Alright, well, let's wrap things up by figuring out the projection of the vector 0, 0, 1, 0 onto the subspace spanned by the following two vectors. Alright, note that the dot product of these vectors is not 0, so these vectors are not orthogonal, so I cannot just simply compute the projection right away. I need to perform the Gram-Schmidt process to turn them into a orthogonal set that has the same span, and thus will be a basis for the subspace. Alright, now there's only two here, so nothing too crazy. We just get our v1, which has to be x1. And we get our v2 by computing the projection of x2 onto the vector v1 and taking the difference. And again, as we noted, the original vector minus its projection is a very powerful tool and has a lot of nice properties. And in fact, will give you something perpendicular to the vector v1. And hey, you can check here by computing those dot products that we indeed will get 0. And we'll have an a minus 6 plus 0 minus 2, which is indeed 0. And now that we have these, the projection of y onto the subspace spanned by those vectors can be computed by computing the appropriate dot products forming the linear combo. And hey, there you go. And again, no promise that the things you get here are visually nice. Right here we've got some unfortunate fractions, but that's just part of the game. Alright, sweet. So, there you have it. A quick rundown of everything that we talked about in the course. More or less. Now, obviously, there were a lot of details that we didn't quite get into that we've previously worked with, but this gives you a pretty good idea of all of the fundamental tools that we discussed about matrices and linear algebra. Thanks for coming along the ride. See you later, Space Cowboy.